Welcome back to our continuation of our discussion of large deformations and geometric nonlinearity. We're going to continue our discussion, having already discussed previously in the last couple of lectures, defining what we meant by geometric nonlinearity and large deformations. We discussed how large are these large deformations, and we determined that sometimes, especially when you're discussing stability of structures, no deformation can be too small. And in fact, very small deformations can lead to large perturbations manifested by instabilities. And we'll explore a few different instances of instability and buckling behavior through a handful of examples in today's lecture. We discussed, when do you actually need to consider geometric nonlinearity? Typically, that's in the context of doing a stability analysis or a buckling analysis for structures, which might be required for doing design. It could also be if you're analyzing and trying to assess when will a structure collapse under some applied loads. And to model that process of collapse, progressive failure, you have to include, most of the time, nonlinear geometric effects. Besides just material nonlinearity, geometric nonlinearity plays a significant role in governing how structures behave under large deformations and collapse scenarios. They can also show up in cables or other types of very flexible structures that deform a lot under applied loads, or maybe structures that move, that have moving components like turbines, or maybe crane arms or other types of robotic systems. So today, we're going to focus in on how we actually model and represent large deformations in an analysis setting. It'll be with a focus on a few particular examples to give you a sense of how these complex representations for nonlinear strain displacement responses lead to nonlinear force displacement relationships, and how we go about solving this in the context of a few representative examples. So we discussed last time how we go about deriving equations governing relationships between displacements of the nodes of some member, let's say, and the resulting nonlinear forces that arise due to those displacements. That nonlinearity, in the case of geometric nonlinearity, can be represented through a nonlinear relationship between strain and displacement. We'll focus in really just on truss elements and take as our basis the expression that we derived several weeks ago for this nonlinear relationship between strain and displacement, use that as our starting point, and then proceed, as we discussed last lecture, in deriving these expressions for internal force and stiffness by postulating some internal strain energy that depends upon this chosen nonlinear measure of strain. From this expression of internal energy, we can use the principle of minimum potential energy, which says that a system in equilibrium achieves equilibrium when the potential energy of that system achieves some minimum state. That's equivalent to taking the first derivative of the total potential energy of that system and setting it equal to zero, its derivative. That gives us our equilibrium equations, which we can solve in a nonlinear iterative fashion. Once we have these expressions for nonlinear forces, we can take their derivative, the derivative of those forces, again with respect to these displacements, the unknown parameters that we're trying to solve for, to obtain our stiffness matrix. And all of this hangs together, and we can prove this just by going through these work type arguments, these energy-based methods. And it turns out all of this is in agreement with Castigliano's theorem. You could think of Castigliano's theorem as being effectively the particular case of minimum potential energy applied when you only have some internal strain energy with an elastic system. So with all that in mind, and knowing that we're starting from this point of view where we're trying to derive these expressions, we have to start from the top. We have to find what is this nonlinear relationship between strain and displacement. I keep talking about it, but let's actually go back and remember, how did we go about deriving the expression for strain in an axial member? So recall, when we were dealing with truss elements, we started from a description of a truss element as being this two-noded linear element connected by two nodes. And if we were to define strain as this constant stretch that occurs within the material, it's some elongation of this rod after it deforms. Maybe both of its nodes might translate a little bit, and you'll get, relative to its initial undeformed configuration, a new orientation of this member, which after maybe rotating a little bit and translating a little bit, it will also have stretched or shrunk a little bit. To measure that relative change in length, we define strain in the usual way. We said strain is just, well, the change in length of this member divided by its initial length. It's a very intuitive way to define strain, right? And we said, well, that's all well and good. We postulated what's the final length of this rod by computing the difference of the two nodal endpoints in the deformed configuration of this truss element. And we computed its magnitude or its norm to figure out what's the overall length of this linear segment connecting x1 and x2 in the element's deformed configuration. We could do that same process to compute what's the length of the element in its undeformed configuration. And from those two quantities, deformed length and undeformed length, we could then come up with this expression. The first box here showing what's the axial strain, this single quantity, which we assume is constant throughout this whole member. But the problem that we ran into when we were formulating expressions for the linearized stiffness matrix of these truss elements, the problem we ran into was that this expression was inherently nonlinear. And by that, I simply meant that the relationship between the displacement of each of these nodes and the resulting strain involved this norm-like expression, which is a square root operation. And inside of it also, there's kind of an inner product going on. So clearly, a square root expression does not lead to a linear relationship between strain and displacement. And we said, well, we can't do that right now. At the time, we said, let's just linearize this expression to come up with some linearized relationship between strain and displacement. And that worked when we said, well, let's just assume that the orientation of this member isn't going to change significantly. When we made that linearized assumption, it said that if this member were to deform somewhat, we could assume that this original orientation, this capital lambda, will be effectively the same as this lowercase lambda after deformation. And if that was the case, then we said all is well and good. We can just use this linearized expression for strain and then proceed in deriving a linear elastic relationship between force and displacement, giving us the conventional stiffness matrix for a truss element as we derived previously. But now let's take a little bit of a different perspective. Rather than linearizing this strain expression, let's hang on to it. Let's keep this expression in all of its nonlinear glory and plug it in to our conventional expression for computing internal elastic strain energy. Remember how we did that? We said, let's integrate the strain energy density over this whole member. So compute the integral over the cross-sectional area of this member and over its full length, the inner product of stress and strain times a factor of 1/2, which effectively is equivalent to 1/2 E times epsilon squared. Carrying out that integral, we get this final expression. Assuming that the strain is constant throughout this whole member, we just get something that looks like this: 1/2 EA times epsilon squared, and then multiplied by the overall length of the member. So now we have an expression for internal elastic strain energy that depends on this nonlinear expression for strain. Implicitly, epsilon is characterizing that nonlinear relationship between strain and displacement. So what happens now? Now that we have a nonlinear expression for the strain in this element, We have an expression for the internal elastic strain energy in this element, which uses this nonlinear expression for strain. Now, what did we do next? We applied Castigliano's theorem. We have to use Castigliano's theorem to take the derivative of this internal strain energy expression with respect to the nodal displacements. In the case of a truss element, that's tantamount to saying, let's take the derivative of this expression with respect to U1 and U2, the displacements of these two nodes at the end of the member. So in practice, if this were a three-dimensional problem, you have three components of displacement at each node, which means taking the derivative of this expression with respect to each of the three components of U1 gives you the resulting forces with three components at node 1. Taking then the derivative of this expression with respect to U2, all of its three components, what we expect to get out is then the resulting internal force that would be applied at node 2. So just by taking the derivative of this expression with respect to these different displacement parameters gives us the resulting or corresponding forces that should be applied at those same nodal locations. Seems straightforward enough, but how do we actually take those derivatives? Well, I'm sure you could certainly go through the trouble of deriving these expressions if you were so inclined, but I won't belabor you with all the details of how these derivations are carried out. The main thing that I want you to observe is that if we have this expression for internal elastic strain energy, we take its derivative. Well, when we take its derivative, we can recognize that a few things are staying constant. We can assume, at least for the time being, that maybe the material properties, the cross-sectional properties, and the overall length, the initial length that is, are relatively constant. So let's just keep them constant. So if we take derivatives of this expression, those quantities will stay the same. But when we take derivatives of this strain-like quantity, in particular, it's epsilon squared. What's the derivative of epsilon squared with respect to these displacements at the ends of this member? Maybe that's a little less straightforward in terms of how we do it. Well, oftentimes, as you would need to do in practice, if you were deriving these expressions yourself, you would usually apply some kind of chain rule of differentiation, where if you're taking derivatives of epsilon squared with respect to displacements, well, in the case of epsilon squared, you would get 2 times epsilon times the derivative of epsilon with respect to the displacements. That manifests in these two equations shown below, where you can compute, if I'm defining this force applied at node 1 as the derivative of this internal strain energy with respect to the displacements at U1, and correspondingly, the force at node 2 is the derivative of this internal energy with respect to the displacements at node 2, I get two different expressions that involve E, A, L, the things that are constant, times the leftover epsilon. The factor of 2 that I got from taking the derivative of epsilon squared happens to cancel out with that factor of 1/2. And I just get something that looks like this: EA epsilon times derivative of epsilon with respect to U1. You can prove that the derivative of epsilon with respect to each of the nodal displacements will give you something that looks like up in the top right-hand corner. It's plus or minus some vector, which is in fact the orientation vector of this member in its deformed configuration divided by the original length of this member. Plugging this in, the final expressions that I get, composing everything together, looks something like this. I can define for convenience this notion of internal force, which is defined in the usual way. I can define what's the internal stress in this member, a constant, as simply Young's modulus times strain to give me stress. And then I can compute what's the internal force in this member, aligned with the axis of the member, as basically just the cross-sectional area multiplied by that stress. Defining this quantity, we find that the resulting force applied at node 1 and node 2 has that magnitude of this internal force. We'll call it F hat. But its orientation is necessarily aligned with the axis of the member. So it is aligned with that vector lambda, the current deformed version of it. And the orientation is further determined by some additional plus or minus sign, depending on which node you're looking at. So for node 1, the resulting axial force applied at node 1 acts in a direction that is parallel to the deformed axis of this member, lambda, and which has a magnitude proportional to this EA times epsilon. So all of this should make good sense to you. It basically says, if we have a truss member, which we assume should only carry axial forces, that is, forces that are strictly aligned with the geometric axis of this member. For that to be the case, we have to define those forces as acting always parallel to the axis of this member, regardless of what orientation it takes, regardless of how much it's rotated or changed in terms of its overall position. To do that, we have to use this deformed axis as the thing that dictates the direction in which those nodal forces act. So in practice, it really doesn't look so different from the way that we defined internal forces in the case of a linear elastic truss element, assuming small deformations. The only difference is this, the axis. In the case of small deformations, if we use that linearized strain assumption, we would basically have to replace lowercase lambda with this original lambda, saying that, well, we would assume that if the axis of this member isn't changing very much, then these forces will actually act along an axis that is parallel to the original undeformed element's orientation. But that stops making sense as soon as this element maybe rotates significantly. What happens if this element rotates 90 degrees? Now, if we said these forces have to act parallel to the original axis, then effectively those forces would be acting in a direction perpendicular to now the deformed axis of this member, which makes no sense. In order to account for that, we have to now put the forces always acting along an axis relative to the deformed configuration of the element. So that should make good sense. Now, what's a little bit more confusing is what do we do when we try to derive a stiffness matrix? And in particular, when we're deriving the tangent stiffness matrix for this particular element. To do that, as I said previously, we have to take the derivative of these force expressions, F1 and F2, with respect to, again, U1 and U2. So in practice, we're taking a second derivative now. It's the second derivative of the internal strain energy with respect to these nodal displacements that gives us the definition of stiffness, which in practice represents small changes in force due to small changes in displacements. To do that, we have to take yet more derivatives, and some of that can get kind of nasty. But in practice, assuming you have the patience and the time to push through all of these different expressions and derivatives, you get something that looks kind of like this. You could go through and basically say, let's take the derivative of these different expressions that we previously derived for the resulting nodal forces. You'll get terms that depend on, if I were to go back, take a moment, and just say, there's really two things that could vary as we take derivatives here. In both of these expressions for F1 and F2, there's F hat, which is the internal force that we assume is always aligned with the axis of the member. And then there's this orientation vector, lowercase lambda. Both of those things implicitly depend on the nodal displacements. So when we take derivatives of both of these expressions, we actually have to use a product rule of differentiation that says, well, there'll be contributions from taking derivatives with respect to F hat, leaving lambda alone. And there will be contributions from leaving F hat alone, but taking derivatives of lambda now with respect to the displacements. Those two contributions lead to two resulting contributions that you can lump together in the final expression for the resulting stiffness matrix of this element. The tangent stiffness matrix now has these terms that, as I said before, are consistent with those terms related to taking derivatives of f hat with respect to the displacements. You get something that looks kind of like this. And then there's those other terms that arise when you consider leave f hat alone in my product rule of differentiation, but now just take derivatives of lambda with respect to the displacements. You get this other term that involves f hat, which we left alone, that provides this additional stiffness term. Now, when you look at these expressions, they may not look quite like the expressions that we derived previously when we were dealing with basically linear elastic stiffness matrices for truss elements. But maybe let's take a slightly different perspective on this. Suppose I were to try to relate this expression that I've just derived with the expression that we've previously derived, assuming small deformations and small displacements. That's equivalent to saying, well, as we mentioned before, just assume that the axis or orientation of the member stays relatively the same. So replace lowercase lambda, the current deformed orientation of the member, with capital lambda, the original orientation. And also, let's assume that we can get rid of that extra term that involves something with respect to f hat. Let's just assume then that f hat, the internal force in this member, is close to 0. If we do that, we recover this expression. And it may not look familiar to you, but if we were to manipulate things around, we could actually show that this is equivalent to that typical expression we had that involved the geometric transformation matrices from global to local coordinate frames in this element. And interior to all of these products would be gamma transpose times some small 2x2 matrix times gamma on the right-hand side. And that 2x2 matrix would look something like EA by L, and then a small 2x2 that involves +1, -1, -1, +1. You can think of this expression as encapsulating all of those different things kind of compressed together, involving the orientation vectors expressed like so. So each one of these sub-matrices now in this 2x2 block structured array, each one of these lambda times lambda transpose components is really a small 3x3 array in the case of a 3-dimensional truss element. Or if it's a 2-dimensional truss element, then each of these subblocks is a 2x2 submatrix. So depending on the size of your problem, the dimensionality, you'll get different sizes. So it all boils down to, well, we could basically go with this expression, make a few modifications or tweaks to simplify it, making these couple of assumptions. And what we get back is the original stiffness matrix that we had previously derived under the assumption of small displacements or small strains. Kind of miraculous, although it shouldn't be too surprising that we should get this expression back. What's interesting, however, is that going back to this fully general nonlinear expression for the tangent stiffness matrix, we have indeed this first contribution to the stiffness matrix that involves EA by L and that small 2x2, +1, -1, -1, +1, except now the orientation is changed. We've just updated the orientation rather than using the original axis of the member to determine how we're determining the stiffness matrix. Now we're using the current deformed axis. But still, what's this second term doing here? What's the deal with this term that now involves f hat? That didn't show up at all when we were considering small deformations. Does this make any sense to include? And what exactly is it doing? To really understand that, we have to consider a particular example. And I love this example. This very simple example that we pondered back when we were saying, let's look at this simple 2-element problem, connected end on end of these 2 truss elements. We tried to analyze it in our MATLAB code and by hand, and we determined that it was inherently unstable when we tried to do this analysis. We couldn't solve it using simple linear structural analysis. But now, we have more powerful tools at our disposal. With the advent of these nonlinear expressions for internal force and these tangent stiffness matrix expressions, we can now actually solve this problem by considering the full generality of geometric nonlinearity. So what happens now in this scenario? We have this two-element assembly. We're applying maybe some transverse load to it, so we're pulling down on it. Effectively, we can assume that this is almost like a single degree of freedom problem. Supposing that maybe this point, this interior node, doesn't displace side to side, let's suppose there's only 1 degree of freedom and it's the transverse displacement, or the sag of this cable, if you like to think of it. It's kind of like representing this simple cable type of structure to which we're applying some transverse load. Simple enough. So how do we characterize then the stiffness associated with this single displacement component? Let's focus in on defining stiffness as really just the transverse stiffness associated with the transverse motion of this node. And let's also determine what's the resulting transverse resisting force associated with that kind of transverse motion. In the case of small deformations, when we made the assumption of small deformations and small strains, there was no stiffness associated with this initial configuration of the member. So there was nothing to resist this node from shooting off to infinity and beyond. But now, suppose that we took this assembly, we applied this force, and let's let this assembly start to deflect. Initially, it will have 0 transverse stiffness. Our initial analysis using linear structural analysis techniques was correct in that regard. Technically speaking, when you have a cable that has no tension in it and you're trying to deform it transversely, when you first start to try to deform it transversely, it will have 0 resistance to that transverse motion. So technically speaking, there should be no stiffness associated with that. But as soon as you start to deflect this cable transversely, something starts to happen, particularly if you're holding the endpoints fixed. What happens? Well, the cable overall is going to deflect downward, it's going to sag, and it's going to stretch out a little bit. Certainly, you can think of the overall length of this cable, if it was equal to 2L, as shown in this case. If it starts deflecting downward, and if that deflection is significant enough, then the overall length of this deformed cable in its sagged configuration is, such that it has elongated somewhat. And you would expect that that should contribute to some increasing resistance to that transverse load. And that's exactly what happens. And that's precisely what our nonlinear relationships between strain and displacement tell us. You can look at it from the perspective of this top graph, where we're plotting what's the resulting resisting force, this F on the vertical axis, versus this transverse deflection U on the horizontal axis. And initially, as you start increasing transverse deflection, there will be effectively no resistance. So the increase in force will be basically flat relative to small changes in U. But as you increase that transverse deflection, the resisting force starts to go up. And it doesn't matter if you're pushing down or if you're pushing up, it'll start to increase in either direction. And it'll continue to increase until it matches with whatever applied transverse load that we put on this cable. So if we wanted to solve this problem, what we're solving for is the equilibrium between that resisting force, F, and the applied force, F bar. So if we were to solve this in an incremental setting, we would basically traverse this kind of S-shaped curve, initially starting out with 0 stiffness until eventually we'll ramp up and hit the target applied transverse load. If we look at the stiffness, what's interesting is right at the initial configuration, we can plot stiffness, transverse stiffness versus displacement. It too will exhibit this kind of interesting U-shaped phenomenon. Think of, again, stiffness is just the derivative of this expression with respect to U. So the derivative of that red curve with respect to U, the single parameter, gives us this U shape. So the slope of that S-shaped curve is initially positive until it reaches sort of this inflection point where now the slope is 0, but then it goes back up and it starts becoming increasingly positive. That's why we have this curve that looks like a U or a parabolic shape. Farther away from this initially straight configuration, you have increasing apparent stiffness of the system, but close to its undeformed configuration, it appears to have 0 stiffness. If you were to run the analysis, basically saying, let's only consider, configurations relative to this undeformed configuration, you'd be saying, let's start at the bottom of this U-shaped curve, which basically says, so stiffness is 0. That's a bad place to start. But if you start departing from that, now stiffness is well-defined. It becomes increasingly stiff, actually, as you continue to deform it. And what's interesting is if we look at why does it become increasingly stiff? It's because, well, 2 things. First of all, consider what would happen if we didn't analyze this original problem relative to its, initially straight configuration. What if we started with this configuration, as shown on the bottom figure, where maybe instead of being perfectly straight, it had some initial kind of ramp? We had a homework problem that tried to analyze exactly this. There were 2 elements connected together, kind of like a triangle, fixed at their bases, and you could assemble and solve this problem without any issues. It assumed that the initial configuration looked like this, and the resulting transverse stiffness would involve a term that looks like 2 EA over L times sine squared of theta, where theta is maybe this angle relative to a horizontal configuration. As theta goes to 0, you approach a perfectly straight configuration, and that contribution of stiffness goes to 0 as well. But there's actually this other contribution. Remember from the previous slide, what's the deal with this extra term? This F hat term that shows up in addition to our regular stiffness contribution, dependent on orientation. It's a force-dependent stiffness. As we increase the internal force in this cable as it's deflecting transversely, there's this extra stiffness contribution that makes the cable look even more stiff beyond just the fact that as you kind of deflect it further, there will be a component of resisting force that can go through these cables, which is not strictly horizontal anymore because the cable is sagging. Now there's a potentially vertical component of internal force in each of these 2 cables to resist the downward force. But also there's this tension stiffening effect. As you increase the tension in this cable, it also has an effect that contributes towards increasing transverse stiffness. And that's actually a little bit more evident if we were to consider a slightly different example. Suppose we still had that initially straight member, perfectly straight to begin with, and we wanted to do the same thing, apply some transverse load to it. But what if we said, let's imagine that we had put some initial strain or some initial tension into this cable, such that now, relative to the initial undeformed configuration, we could compute what is the contribution to the initial stiffness of this system, assuming that it had some initial tension in it. This tension stiffening effect effectively gives you something that looks kind of like this for your initial stiffness. Or in other words, we have stiffness that depends on internal force. That makes good sense, right? If you were to take a cable, if you were to stretch it a little bit, and then try and repeat your same experiment as done before, in its stretched configuration with some tension in the string, now try deflecting it. Initially, it will actually feel like it's going to resist whatever transverse load you're applying to it. That's the transverse stiffening effect. It says that if I include some tension, then I actually have some initial stiffness. That actually comes to play in all kinds of different settings, as in the case of stringed musical instruments. If you take some kind of string on like a guitar or something, to tune these instruments, what you're doing is you're actually increasing or decreasing the amount of tension in one of these cables or one of these strings on a guitar, for example. And what happens? At different levels of tension, the string will actually exhibit a totally different transverse stiffness. That transverse stiffness, if you're familiar with concepts from structural dynamics, that difference in transverse stiffness will lead to a different natural frequency of vibration of the spring, of this string, such that increasing the tension in this string increases its transverse stiffness, which increases the frequency at which it vibrates, which correspondingly influences the frequency that we hear when you play that different string. So if you increase the tension in one of these guitar strings and you keep plucking the string, what you'll hear is a pitch or a frequency that continues to increase. And what you're hearing is that tension stiffening effect. Kind of cool, kind of crazy. If you have an instrument at home or if you play something, go ahead and go try this. It's actually pretty cool. In any case, the tension stiffening effect kind of guarantees that you're going to have some initial stiffness relative to an undeformed configuration. And that can be really important if you're trying to model cable-type structures, which might otherwise be unstable if you assume that the cables in that system are perfectly slack to begin with. Starting out with perfectly slack cables, zero initial tension, could mean that you can have that situation as shown in the previous problem. Initial configurations of the structure might then look unstable from that starting point. But if you said, well, let's put a little bit of initial tension in the system, now you're all good. Now, if you're running with geometric nonlinearity and you have this tension stiffening effect, then the system actually is inherently stable to begin with. That's really important, especially if you're trying to model structures that have cables. But what happens if the opposite were to be true? What if instead of putting some initial tension in this system, what if we put it into an initial state of compression? So consider yet again the same example, but let's suppose that rather than maybe stretching that string a little bit, what would happen if we tried to compress it, put it into some initial state of compressive force? What would happen then? Well, the tension stiffening effect still is present, but the sign of that force being negative now implies that in this initial configuration, the initial stiffness is now not just zero, and it's not positive anymore. Under compressive loads, it can potentially become negative. And that negative contribution to stiffness, transverse stiffness, implies that the structure is not just, not just unstable, but like really unstable. To the point where this structure, if it was initially straight, is not going to want to stay that way. Even though, let's suppose we took away that transverse load. Let's suppose we just kept this kind of like simple two-node or two-element problem as is, no transverse load, but we put in some initial compressive force. Even though, technically speaking, if I'm not applying any transverse load, this structure is in a state of equilibrium, somewhat bizarrely. And that makes good sense. If I'm putting it into compression and there's nothing that's perturbing it away from this perfectly straight orientation, technically speaking, hypothetically, this should be perfectly admissible. It's an admissible solution that satisfies the equations of equilibrium, right? But in practice, that's not what really happens. You all know what really happens. If you were to take this string and try to compress it, it's going to buckle, it's going to sag, or it's going to experience something that deforms it away from that initially straight configuration. Because it can't sustain this compressive load. And the reason has to do with the fact that as you compress it, the apparent stiffness of the system becomes negative. What happens when you have a negative stiffness? It's sort of an unphysical situation, but that's what the math is telling us. The math says we take the derivative of this kind of S-shaped curve, which is now even more curved. It says, really, with zero external applied loads, there are three possible equilibrium states. One, which corresponds to this unstable configuration of a perfectly straight two-element problem like shown in the figure top. And there are two potential equilibrium configurations involving some kind of jump or displacement of the structure away from that perfectly straight configuration, either vertically or downward. Either of those configurations correspond to a state of zero transverse applied load, and 0 apparent internal force within this kind of assembly. Curiously, which one of these do you think will happen? Will it deflect upward? Will it go downward? Or will it stay perfectly straight? What do you think? You say downward. I think that makes a lot of sense, right? If there's gravity is going to pull it downward. There's always going to be a little bit of downward force. Even though I've not shown any kind of external force applied here, there really should be some residual like self-weight that's pulling this thing down. So in general, yeah, I would say that's probably a good intuitive answer. It should deflect downward. But what if we're in some mathematician's daydream, and he's thinking, oh, maybe we're in space in some vacuum, I don't know. And what if there really are no other external forces? If there's really nothing to prevent it from going up or down, and it has no preference one way or the other, it's hard to say which way it will really go. I mean, there's no unique solution to this problem, right? This is really the issue, coming back to the problem of well-posed boundary value problems. I know you don't like hearing about boundary value problems, but bear with me. When we posed well-posed boundary value problems, we insisted on 3 things, right? The solution has to have a problem or a solution to begin with. It has to have a unique solution, more than just a solution. And the problem has to be stable. Clearly, this doesn't look stable. But does it even have a unique solution? Not really. There's multiple possible admissible solutions to this problem. In fact, this is really not a well-posed problem for that very reason. It doesn't have a unique solution. That's kind of the issue when you start delving into this domain of, well, I can now simulate these problems that have instabilities inside of them. But even if I can simulate it, should I really be doing this if ultimately I'm setting up a problem that doesn't have a unique solution? Which one do I go with? This is sometimes referred to in mathematics as a solution bifurcation, where it's not that there's just one possible solution, but there may be many admissible solutions. And in these situations, you no longer have a well-posed problem. That's a little bit disappointing. Do you have a question? The energy function for this? Well, you could think of energy as being maybe the integral of this F curve. But interestingly, yeah, let's give it a shot. Let's try to sketch what this looks like. Hopefully I don't mess it up. So suppose we wanted to represent the internal or stored elastic strain energy of this system. It's really the integral of this kind of S-shaped curve, right? It should look something kind of like this. It doesn't matter whether you shift it up or down, but it'll look kind of like this. It'll look like, there should be something like this, maybe like that. It should look kind of like a W, right? And if we go, interestingly, by the principle of minimum potential energy, the principle of minimum potential energy says that this system will be in equilibrium when we achieve minimum potential energy. If this is potential energy, minimum potential energy occurs either here or here, which is basically exactly where this S-shaped curve passes through the x-axis. But there's another point. There's another inflection point here. It's a local maximum, but it is nonetheless a location where the slope of the potential energy function is equal to 0. In fact, there's a possibility that there may be multiple non-unique solutions corresponding to these inflection points, or basically points at which you would have otherwise this force equation, passing through the x-axis, or the roots of this function, if you like. So that's kind of one way that you can think of it. And the problem is, you have these potential energy wells, if you like to think of them as such. If you think of like there's a ball fictitiously rolling along this curve, it's going to try to find the low points, right? But if you started right here, which way is it going to roll down? Is it going to roll to the left or to the right? Is it basically going to deflect up or down? Who's to say? Who's to say? Well, Let's consider a slightly different but related example. What happens if you have, let's say, a structure initially stable, some kind of vertical orientation where there's a kink, initial kind of angle of inclination of these members, such that there's an initial stiffness associated with this configuration. Under some applied vertical loading, maybe I load it transversely in the vertical direction, this arch will deflect downward. We can run these types of problems in a linear elastic setting, no problem. Okay. And we can load this problem up, increasing the amount of load successively up to a particular point. Imagine what happens if you have this arch. And assuming that all the material behavior is elastic and everything, suppose you took that external force, you increased it, and the arch keeps compressing downward and downward and downward. And what happens as it continues to deflect downward? It'll approach more of a straight configuration, meaning that its apparent stiffness will be decreasing as its arched configuration goes down. And there'll be this competing or contributing effect of the tension stiffening. It'll continue to be in compression, and increasing compression will lead to continual loss of apparent stiffness, transverse stiffness of this arch structure, until eventually you'll reach a critical point where the stiffness of this arch, once you apply a critical load to it, will become zero. And at that point, you have a phenomenon sometimes known as snap through, or buckling if you like, but it's a particular type of buckling. Snap through buckling is really precisely related to this phenomenon where you maybe have a structure that is initially stable relative to some kind of configuration. You apply some load, and at some critical load, you determine that there's this instability that happens that converts the structure from one initial configuration to now this kind of deformed or snapped through configuration. It's kind of like those little rubber toys that you can play with, those caps that you can invert, place on a table, and then they kind of snap through and then pop up off the table. Kind of a fun experiment. If you can find one of those, go ahead, try it out. You'll witness snap through buckling in action. But what's interesting is that after you apply this load, after snap through occurs, now you revert into, again, a stable configuration of the structure. And as you continue to load it, if you were to continue to load it, you would notice that, well, the stiffness of the system will now continually increase, because now not only is the system in tension rather than in compression in its previous vertical arch configuration, now you're also, increasing stiffness just by changing the orientation of these members to be further, away from parallel. So as that happens, throughout this whole process of snap through buckling, what's most fascinating is that if you were to do this experiment, load up this arch up to a certain point, up till it reaches that critical buckling load, it'll snap through. And what's curious is that if you were to then take whatever load you applied to that structure and remove it, you would find that the structure is now permanently in this new configuration. Rather than a vertical configuration, it's now in this reflected kind of downward configuration. It'll stay that way, almost as if you've permanently deformed or changed the configuration of the structure. To do that, to permanently change the configuration of how the members are organized geometrically, you have to put energy into this structure. You have to dump energy into this system, and it looks like the system is eating up all of that energy somehow. To change the configurational energy of the structure, which is related to its inherent geometry, you have to put energy in. But it's not like the energy is being dissipated through plasticity or any other of these mechanisms that might happen at the material level. So where is that energy going? If it's not going into plasticity, and yet we're saying, let's do this problem, let's do a snap through buckling problem, we seem to lose energy in this process of snap through. So what happens? Where does it go? What do you think? What would happen in real life if you were to do this snap through buckling example? What would happen to the structure immediately after it snaps through? Yeah, there'd be some transfer of load, perhaps, but some other things might happen. And in particular, if it's going to happen quickly, yeah, you kind of had this, fluctuating behavior. If it happens quickly, and really snap-through buckling is an instantaneous phenomenon, at least according to our analysis in a quasi-static setting. For snap-through buckling to occur, the structure has to go from here to here in basically a split second, if that, instantaneously. There's no way in the laws of physics would permit the structure to go from here to here in effectively 0 time. The inertia of the structure should technically constrain it from instantaneously reverting into this alternative configuration. Where this energy goes, it goes into vibrational kinetic energy. Technically speaking, it gets converted from stored elastic strain energy that's built up in this member, and all of a sudden, that energy is released into vibrational energy. When you have snap through, technically this member should be vibrating, fluctuating. But we haven't accounted for inertial effects. We haven't done dynamics in this class. How can we do that? Is that even allowed? Well, this is probably one of the most frustrating things that I see. So many people try to solve these types of bifurcation types of problems involving snap-through buckling and other types of instabilities and buckling analyses. They have so many sophisticated solver techniques, nonlinear solvers dedicated to solving precisely these types of problems, presuming that these systems can be analyzed using quasi-static analysis. But that's just not right. It doesn't incorporate an important aspect of the physics, dynamics. It just doesn't make sense for the structure to deform in this way instantaneously. So if you're modeling structures that behave in this way, that exhibit instabilities and undergo buckling, you really ought to be considering that this is not a quasi-static process. It is a dynamic process inherently. And the only way that you can reliably run these problems and get a unique, well-posed boundary value problem with unique solutions, you really should be using dynamics, to be quite honest. And while you might say, well, really, even if it behaves dynamically, it's going to vibrate. There'll be other dissipation mechanisms. There'll be air resistance that kind of eventually slows it down. Or maybe there's a little bit of viscoelastic behavior in the material, or kind of like friction in the joints of the structure that eventually will damp out all those oscillations and it'll reach a quasi-static state. But really, if you wanted to model those things, you should be representing them in your physics and how you're idealizing the problem. So bear that in mind. When you're trying to solve these buckling type problems, you might be actually trying to solve an ill-posed boundary value problem. Just be careful. I think we've gone a little bit over time, but if there are any questions at this point, feel free to ask. I think this wraps up our discussion of snap-through buckling and other types of related phenomena for truss elements. All right. If no other questions, feel free to go. I'll see you guys on Monday.